In this video, we will review orbital hybridization before we move back to resonance in part 2 of this lecture. The electron configuration for hydrogen is 1s1, meaning that the 1 electron of the hydrogen atom resides in a 1s atomic orbital. Recall that s orbitals are spherical in nature, and I'm representing 1 electron in the 1s orbital by drawing an arrow. Hopefully you remembered this notation from general chemistry. When hydrogen forms a bond, its 1s orbital overlaps with an orbital of another atom. We will come back to this idea shortly. A carbon atom has a valence electron configuration of 2s2 meaning that its 4 valence electrons reside in the 2s and 2p atomic orbitals. The 2s orbital is, of course, spherical as well, and recall that there are 3 redundant dumbbell-shaped 2p orbitals, one in the x-plane, one in the y-plane, and one in the z-plane. Using our arrow notation, we will place one up arrow and one down arrow in the 2s orbital to indicate 2 spin-paired electrons. We will also place one up arrow in 2 of the 3 2p orbitals. It does not matter which 2 we choose, as all 3 are energetically equivalent. The remaining p orbital will not be occupied. When carbon forms bonds, it does not use its 2s or 2p orbitals directly. Instead, it uses the 2s and 2p orbitals to make hybrid orbitals. Let's take a look at a few examples to illustrate. First, let's consider a carbon atom with 4 groups around it, like CH4. Each hydrogen is one group. In this situation, carbon will use all 4 of its valence orbitals, the 2s, the 2px, 2py, and 2pz, to form 4 new hybrid orbitals. Each of these hybrid orbitals will be composed of 1 part s orbital, or 25%, and 3 parts, or 75%, p orbital, and will have a shape that reflects this composition, a somewhat spherical dumbbell shape. These new orbitals are called sp3 orbitals to indicate the 1 part s, 3 parts p composition. The reason that carbon adopts this hybridization pattern is to minimize electron repulsion. So hopefully you remember from general chemistry that valence shell electron pair repulsion, or VSEPR theory, predicts that a central atom with 4 groups around it will adopt a tetrahedral shape, and all 4 of the groups will be about 109.5 degrees apart from one another. In our CH4 example, each sp3 hybrid orbital of carbon overlaps with the 1s orbital of a hydrogen atom to form a sigma bond. A couple of notes about the drawings here. We are using thick lines to indicate the orbital is coming out of the plane of the computer screen or towards you, and dashed lines to indicate that the orbital is going into the plane of the computer screen or away from you. We will also be using an abbreviated version of the hybrid orbitals as shown here. This is just to keep the drawings a little neater. When carbon has only 3 groups around it, the atom will adopt a trigonal planar geometry. It does so by using 3 of its 4 valence orbitals, the 2s orbital and 2 of the 2p orbitals, and it will generate 3 sp2 hybrid orbitals. The remaining 2p orbital is left unhybridized. The composition of the sp2 orbitals is 1 part, or about 33%, s orbital, and 2 parts, or approximately 67%, p orbital. The hybrid ends up looking similar to the sp3 orbitals, but it's a little more spherical in nature because the increase in %s character. Take this molecule for example. Each carbon in the molecule is surrounded by 3 groups, 2 hydrogen atoms and 1 carbon atom. And each carbon will be sp2 hybridized. In this example, 2 of the sp2 hybrid orbitals on each carbon will overlap with a 1s orbital of a hydrogen atom to form 2 new sigma bonds on each carbon atom. We will notate this orbital overlap and bond formation as sigma colon CSP2-H1s. The third sp2 orbital will overlap end to end with the other sp2 hybridized carbon atom to form a sigma bond between the 2 carbons. We will notate this orbital overlap and bond formation as sigma colon CSP2-CSP2. The bond angles between the 3 groups on each carbon atom are all about 120 degrees, as we would expect for trigonal planar geometry. The 2p orbital that was not hybridized on each carbon will be used to form the pi bond. The 2 unhybridized p orbitals will overlap side to side to form a pi bond that is orthogonal to the sigma bond. The overlap here is indicated with horizontal lines. And we're going to notate this orbital overlap and bond formation as pi colon CP-CP. Finally, when carbon is surrounded by only 2 groups, it adopts a linear geometry by using sp hybridization. So 2 of the valence orbitals, the 2s orbital and 1 of the 2p orbitals, are hybridized to form 2 new sp orbitals, and the other 2 2p orbitals are left unhybridized. The composition of each of these sp orbitals is 1 part, or 50% s, and 1 part, or 50% p orbital. So the shape of the sp orbitals is even more spherical than the sp2 due to, again, an increase in the s character of the orbitals. Acetylene, which has a carbon-carbon triple bond, is an example of 2 carbon atoms that are each surrounded by 2 groups, 1 hydrogen atom and 1 carbon atom. 1 hybrid sp orbital of each carbon atom overlaps with the 1s orbital of a hydrogen atom to form a sigma bond, and we will notate this orbital overlap and bond formation as sigma H1s-CSP. The second hybrid orbital of each carbon atom overlaps with the sp orbital of the other carbon to form a sigma bond, and we will notate this overlap and bond formation as sigma colon CSP-CSP. The bond angles in acetylene are about 180 degrees, as we would expect for linear geometry. The 2p orbitals that were not hybridized on each carbon will be used to form the 2 pi bonds. The pi bonds are both orthogonal to the sigma bond, and they're also orthogonal to one another. We will note the pi bond formation and orbital overlap as pi colon CP-CP. And here again, we're using the thick lines to represent the orbital coming towards you and dashed lines to indicate the orbital going away from you. So to recap, when carbon has 4 groups around it, it adopts a tetrahedral geometry by forming 4 sp3 hybrid orbitals. When carbon has 3 groups around it, it adopts a trigonal planar geometry by forming 3 sp2 hybrid orbitals. And then it has a p orbital that remains unhybridized that can be used to form a pi bond. And then finally, when carbon has only 2 groups around it, it adopts an sp hybridization and leaves 2 p orbitals unhybridized that can then each form a pi bond. So a few notes about bonding and hybridization. Recall that the carbon-carbon bond of ethane is composed of just a sigma bond that's formed from the overlap of 2 carbon sp3 orbitals. The sigma bond between the 2 carbons in something like ethene, when we have a double bond, is different because it is formed from the overlap of 2 carbon sp2 orbitals. And then finally, when we have the carbon-carbon triple bond, the hybridization of the carbons is sp, so the sigma bond is formed from the overlap of those sp orbitals. And also recall that as you increase the %s character, going from sp3 to sp2 to sp, that the higher %s character means that the electrons are going to be pulled in a little tighter to the 2 carbon nuclei, and therefore there's going to be a contraction in the carbon-carbon bond length. Similarly, as the %s character of an orbital increases, the strength of the bond also increases. And you can observe those same trends for the carbon-hydrogen bonds. When the carbon has a higher %s character, the carbon-hydrogen bond will also have a shorter bond length and will have a higher bond strength.